Welcome back to our channel. In today's video, we'll be diving into the intriguing topic of p-values and their significance in scientific literature. Have you ever wondered why the p-value is so successful in research? Well, we are here to shed some light on this matter, so let's get started. As the statistician Benjamini 2016 noted, the p-value offers a crucial first line of defense against being fooled by randomness. It helps us separate signal from noise in our data. Especially, p-values tell us how surprising the data is, assuming there is no effect. Now, let's consider an example to better understand the concept. Imagine we are investigating whether driving while calling increases the risk of a car accident. When analyzing the data, we compare the differences between the two conditions. If we find a difference, say 0.11, we need to determine its significance. So, when facing such a difference, what does it mean? Is it just a random noise or a real difference? Let's explore our options. Probably just random noise, probably a real difference. To answer this question, we perform a statistical test. We calculate a test using the mean, standard deviation, sample size, and compare against each other. Here are two charts. The first chart shows a p-value greater than 0.05, indicating the observed data is not surprising. On the other hand, the second chart displays a p-value less than 0.05, suggesting that the data is surprising. Okay, this is also calculated from mean, standard deviation, and their sample sizes. We calculate the test statistics and compare it against a distribution. But what is exactly a p-value? Let's delve into the details. A p-value is the probability of obtaining the observed data or more extreme results, assuming the null hypothesis is true. It represents the probability of data, not the probability of theory. It's important to note that p less than 0.05 doesn't imply a 95% likelihood of the effect being true. For instance, it doesn't imply precognition. If you study precognition and you find it is statistically significant, does it really mean that the person has a precognition? So, after p is less than 0.05, an effect is not 90% likely to be true. And you can't get the probability the null hypothesis is true given the data from a p-value. For example, probability of data given the hypothesis is not equal to probability of hypothesis given the data. If p larger than 0.05, the data we have observed is not surprising. P greater than 0.05 does not mean there is no true effect. To really detect the small effects, you need large samples. To help you remember the interpretation, here's an interesting analogy. A monk once asked a Chinese Zen master, "Has a dog Buddha nature or not?" The Zen master replied with the character M, which means no or not. In a similar vein, we can think of p greater than 0.05 as representing no or not surprising. M, you do not know. Now, let's discuss how to use p-values correctly in our research. P-values can guide our behavior in the long run. If p-value is less than alpha, typically 0.05, we can act as if the data is not just noise. On the other hand, if p is greater than alpha, we should remain uncertain or act as if the data is noise. So, meaning that when you act as if there is an effect when p is less than 0.05, in the long run you won't be wrong more than 5% of the time. Interpreting p-values correctly is crucial. Let's explore some common misinterpretation and better ways to approach them. Instead of saying we found a p-value of less than 0.05, so our theory is true, we should say we found a p-value of less than 0.05, so our data is surprising. or our data shows something. It is essential to understand that after p greater than 0.05, we might enter what's called a degenerative research line. However, we must remember that p-values can vary, and thinking meta-analytically helps gain a broader perspective. So therefore, statistical tests should be used with discretion and understanding, and not as instruments which themselves give the final verdict. A phenomenon is experimentally demonstrable when we know how to conduct an experiment, which will rarely fail to give us statistically significant results. Or Fisher 1937 said, "No isolated experiment, however significant in itself, can suffice for the experimental demonstration of any natural phenomenon." So, let's explore the p-value distribution when there is true effect, and also explore when there is no true effect. When there is true effect, the p-value depends on the statistical power. Conversely, if there is no true effect, it is uniformly distributed. But if you look at the two graphs, p-value distribution with 50% power and 80% power and 90% power, you can see that the p-value, the chance of p-value being less than 0.05 is increasing as the statistical power increases. So when there is no effect, which p-values can we expect? We said p-values are uniformly distributed. This usually means that you can expect a wide range of p-values and they don't provide evidence for a real effect. And most importantly, the chance of p-value being 0.03 and 0.98 is equally probable. So if you have no effect, so you expect a p-value with a uniform distribution. And that's a wrap on our discussion about p-values and their significance in scientific literature. We hope this video has given you better understanding on this statistical concept. Remember, p-values should be used with discretion and understanding, not as a final verdict. As the great statistician Neyman and Pearson once said, they are tools that guide us but don't give the ultimate answer. If you are interested in learning more, we highly recommend checking out the book Improving Statistical Inferences by Daniel Lakens. Additionally, you can find a course on this topic titled Improving Statistical Inference. Thank you for watching and stay curious.